Okay, so Taylor series and Maclaurin series. So let n equals 0 to infinity of Cn times x minus a to the n be a power series with radius of convergence r bigger than 0 and interval of convergence I. So therefore it converges for r bigger than 0, where x is in R. Now, for each x, here we go, in where x minus a is less than r, the series converges to a finite value. The series may therefore be defined as a function of fx equals n equals 0 to infinity of Cn times x minus a to the n with domain I. Now, I'd like you to note also, they're using that notation now, but however later, we call this here we call that the Taylor series, and they often use Tn, where n is 0 to basically whatever value is here, so which is a bit hard when it's both n. But basically, they put here the maximum value they want n to be. So we'll just put this for now. But basically, what we're going to see is that, like T5, for instance, maybe I should have put, you know what, I probably should write that differently. Let me just show you what I mean. For instance, if I say Tk is when n is 0 to k of that, so that's going to be the Taylor series version. So for instance, T5 would be C0 times x minus a to the 0, then C1, and then C all the way up to C5 times like x minus a, all the way up to x minus a to the 5. Oops. Anyway, we'll get there in a second. But I just noticed they kind of changed the format of the notation out of nowhere in the notes. Anyway, I'll show you what I mean. Functions defined in this way may look awkward. However, as we've seen, a convergent power series can be added, differentiated, and integrated, just like ordinary polynomials. So polynomials with x's in them. They are very useful because we can express many different functions as power series expansions. So let me show you. Suppose fx is n is 0 to infinity of Cn x minus a to the n. Then expanding that out, you get C0 times x minus a to the 0, which is 1. C1 times x minus a to the 1. C2 times x minus a to the 2, all the way to infinity, or just keep going. Where x minus a is less than the radius of convergence. Since we can differentiate the power series on an open interval contained in I, so within the interval of convergence, we can differentiate it. When you differentiate it for one time, you get C1. The CO goes away because there's no x value in that, right? So here, the derivative of x minus a is 1, so 1 times C1 is just C1. Does that make sense? For this one, we put the 2 to the front, so we 2C2 times x minus a to the 1. Then 3C3 times x minus a to the 2, and so forth. Does that make sense? But if we differentiate again, second one, we'll just get 2C2 because the C1 goes away because it's a constant. And then here, when we differentiate this term here, we get 2 times 3 is 6, C3, x minus a to the 1, and so forth. So we get interesting things happening when we keep differentiating. Now altogether, f to the nth derivative is n factorial over Cn. Let's think about that for a second. Maybe we should look at the third derivative as well. Okay, so this one here becomes, what's the derivative of that term? The one I'm pointing to, this one. Just 6C3 because, but you get it, yeah. Now, I might write in the next term. What would the next term have been? I believe if the term after this would have been 4C4 x minus a to the 3, then what would the next term be? This term in the second derivative. 12C4 x minus a to the 3. Oh, sorry, 2. Is everything okay so far? So I want you to just think about, for the third derivative, I get just 6c3, and then my next term is going to be, I'm after this one, the one after this one. Okay, so let me see now if I can, and it'll keep going, but let me see now if I can make sense of the next line. N factorial Cn is 1 factorial C1, and that is 2 factorial C2, because 2 factorial is 2. And this one here is 3 factorial C3. 3 times 2 times 1. So, okay, that makes sense. Next one. N plus 1 times Cn plus 1. This, okay, here, n is 1. Here, n is 2, okay? Because that's the nth derivative. Is everyone okay? So for this one, n plus 1 is 2. 2 factorial is 2. And then we just get c of 2, and then x minus a. That works with that, okay? The next term in the second derivative, n plus 1 is 3. 3 factorial times c3 times x minus a. Yep, that works there too. Are you getting what I'm saying? Yeah. And it also works here. Here, n equals 3. So n plus 1 is 4. That is 4 factorial. Do it in your head. 4 times 3 is 12. 12 times 2 is 24. And they got c4, x minus a to the 1 again. So do you see how this does in fact work? Okay. Now, I want to use the above formulas to find f of a. Oh, let's back up here at f. What is f of a? Have a think. Yeah, and what happens? It's just the constant c0. Because this goes away and this goes away because the a minus a is 0. Right? Yeah, that's it. F dash a, c1. Because this goes away and this goes away, you're left with the constant. You're always left with the constant. When we're substituting a, is everyone okay? Yeah. Yep. F double dash a, second one. 2c2. Do you see how that is? Yeah. All right. Let's just do one more. D. F to the 3, F's third derivative. Let me try that again. The third derivative of f at a, 6c3. So, and it's important to note, girls, that these coefficients of c could be written in factorial notation. For instance, this one here, is that technically 0 factorial times c0? Yeah, 0 factorial is 1. Is this one 1 factorial c1? Is this one technically 2 factorial c2? And this is technically 3 factorial c3. Beautiful. So basically, to D, the nth derivative of f at a equals Cn. So that's something that's very important. Is everything making sense? So that now helps us realize that we can rearrange this and divide both sides by n factorial and realize that Cn equals the nth derivative of f at a over n factorial, which is written here, where you got to remember 0 factorial is 1, and f0 is, like this 0th derivative is just f. It's just not being differentiated at all, 0 times, so you just got to remember that. So basically now we have a formula for this constant that's always at the front of the power series. But that's only for Taylor series. Right. We can use this information to reconstruct the function f in terms of its values of its derivatives evaluated at x equals a. So now we're getting rid of the c's and replacing it with this, what we just found. Okay? So for the first one, if you remember, it's c0, but that actually ends up just being the number 1. So fx equals f of a times f dash a over 1 factorial, which is just f dash a, times x minus a, plus f double dash a of 2 factorial, x minus a squared, plus f triple dash a of 3 factorial x minus a cubed, and so forth to infinity. And this is the Taylor series. It goes to infinity. It equals k, from k is, now they've changed it to k all of a sudden. That is essentially the Taylor series. Now, when we let a be 0, though, to make it a bit simpler, And so we just get x and x squared and x cubed and x, because it's x minus 0. That's called the Maclaurin series. So the only difference between Taylor series and the Maclaurin series is that A is 0. It's just a simplified version. And remember that A, it's all about that radius of convergence. Do you remember that? Usually it's like x minus A is less than some 1 or whatever. And so the Maclaurin series happens when you just get x. And remember, that's from the ratio test. So all this links in. Also, girls, look, when we had f of a and f dash of a and f double dash of a, we now have f of 0 and f dash of 0 and f double dash of 0 and so forth, which is kind of simpler as well, which is nice. Is everything okay? The last one is like the general term, but it's not something I would really learn. I'd kind of more think of it like this. Is everything okay? Cool. Now, we have shown for a function of fx with domain I that if f has a convergent power series for x in the interval, and the derivative of f for all orders exist on I, so in other words, I can keep differentiating it enough, or I with its endpoints removed if I is closed. So remember how it's differentiable in the open interval? And I think that's to do with the tangents not being defined at the ends. Then f has a Taylor series representation, and this is the only power series representation of f. However, we still need to consider the conditions under which the power series representation of f will converge. This here kind of says if the kth derivative of f exists at x equals a, then for k is from 0 to n, then the nth degree Taylor polynomial approximation of f about x is a is this. This is important notation, this Tn. Tnx of, notice we don't go to infinity anymore. The highest derivative and highest power now is n, and the bottom is n factorial. So that's the main difference here. Consider the function fx equals e to the x. Now, wait a minute. Oh, that's really good because the derivative always exists. You can differentiate that an infinite number of times. Technically, you don't always have to be able to do it an infinite number of times. You might just need to be able to do it, say, 6 times, depending on the degree of the Taylor polynomial. So f to the nth degree is just e to the x, and it exists for all of n in z, and x is in R, and fn is of 0 is always e to the 0, which is 1. So this is no problem, we can work with this. So write down expressions for the following Taylor polynomials about 0. In other words, a is 0. So technically they're Maclaurin polynomials. But anyway, always start with f of a, or in other words, f of, in this case, 0. So that's when we're not differentiating at all. Then we go first derivative. Technically, what are we dividing it by? 1 factorial. But that's just 1. And then what am I timesing it by? What do we usually times by? X minus a, but since a is 0, it's just x. Okay, now we're going to get more interesting. F double dash of 0 still over 2, technically factorial, but yes, 2 is correct, times x squared plus f triple dash or over technically all 6, yes, exactly. I wanted 3 factorial, but all 6 would be correct. Okay, I'm going to go dot, 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 because technically we can still go into infinity. Or technically an unknown value of n. Girls, can you help me write this as a sum? So they used k. So where does k start from? What are we going to? Now, I may have made you say that. Basically, it's n. We just don't know what n is. For all we know, it could be huge. Yep. And how can I write this as a general expression in terms of k? Take a moment. F to the kth degree. Of 0. Yep. That's okay. What else would you put? Yep. Times. Beautiful. And that's our general expression for this. However, girls, I just realized I forgot something. I could have been finding f of 0 all this time. What's f of 0 and f to the nth degree of 0? In this example, 1. So now I'm not going to rub it out. It's all good. So, but I'm glad we did that because that's like the general, right? The general formula. So now let's do it, be more specific. This part here is always e to the 0 for this function. And e to the 0 is 1. So what's an even easier way I can rewrite all that? Just x to the k over k factorial, which is very nice. All right, so now that we've done that, let's answer the rest of the questions. What's t1 of x? What do I do? This is the sum. You don't have to write this line, but just to explain it, this is the sum from k is 0 to 1. There's going to be 2 terms of x to the k over k factorial. So when k is 0, what do I get? 1. And I'm just going to go a little slower. X is 0 over 0 factorial, which you're right is 1. What's the second? And it's plus, because it's a sum. What's the second term when k is 1? Which is? Just? Thank you. Okay, and now I want t2x, which is just one more term than the previous. So what is that? 1 plus x plus, take a moment. I'm doing x squared over 2 factorial, which is 2. Tell me what is the next term. Beautiful. Tell me what's the next term. Beautiful. Now let me just go a little slower for people watching at home. Just to note, we're starting at 0, and this is when k is 1, this is when k is 2, this is when k is 3, this is when k is 4. Oh, girls! Wait, 1, 2, 3. Oh, I've missed one. So when k is 5, what do we get? 120? Yep. So that's when k is 5. So that's good. Basically, girls, if it's t5, how many terms should I get? If it's t2, how many terms should I get? So n plus 1 terms. Below are the graphs of the polynomials in the previous question. So girls, this dashed line is t1, which was 1 plus x, just a line. Is everything okay? T2 is a quadratic, so it's this dark black parabola. T5 is this something that kind of looks like a cubic. It's actually a quintic. Anyway, girls, but the thing is, they're just Taylor polynomial approximations to the original function of fx equals e to the x. What I'm hoping you notice is that, first of all, t1 was nothing like fx, e to the x. Like it was just a straight random line. At least it's going in kind of the right direction though. It's like an increasing function, which e to the x is as well. Then t2 became like a bit more curvy. So it definitely matched it more in this area. In this area. Everything okay? Then T5, damn it, is looking even better because it's matching it more in a bit more, but then it matches it like up to here almost. Because again, I'm comparing it to this dashed black line. So, but the point is, as the degree of the Taylor polynomial increases, we actually get closer and closer to the real function of fx equals e to the x. As n increases, t and x starts to approach the curve of y equals fx. The curve of t and x is more like fx about x equals a, which equals 0 in this case. So just notice that, girls. We used an a value of 0, right? For all the tn's, we hit the right value for f of 0. Around this value of x, all the functions were quite close to fx. But then as we moved away from, here, f of 0, or 0, x is 0, we got further and further away from the function. It's kind of like because the error is at a minimum around a. If we denote the error, Rn, which is like the error of the nth degree Taylor polynomial, of x to a, to be the error involved using the Taylor polynomial degree n, that's what that says there, To approximate fx about x equals a, notice that, to approximate fx about x equals a. So in other words, these Taylor polynomials, again, work really well for x around a. In the last case, that was when x around 0, which is why all the Taylor polynomials were really good around there. But then they started to deviate further away from 0. Now, on the interval of convergence I, then fx, the actual function of fx, equals the Taylor polynomial plus the error. It's like whatever's missing from the Taylor, if we add that on, that function on, we get the original function. The graphs for the case of fx equals e to the x expand about x equals 0 suggest that as n increases, that error decreases and Tn x becomes closer to fx. So that's what we were saying before. The error decreases, therefore the Taylor polynomial gets closer and closer to the fx. Consider a function of f with domain I containing x equals a, but it's not an endpoint. Suppose the n plus 1th derivative of x exists. Then for x in I, the Taylor formula with remainder of Rn x plus x to a that's the Taylor polynomial. We've already been working with this, that's fine. And now the remainder, the next term, like look at these two, compare them. The way I see it, it's kind of like the next term in the Taylor polynomial that we didn't include. And that one's going to be bigger than all the remaining terms to infinity. So my point is, it's like because that next term is the biggest part of the error, they've taken just that term because we can't do it to infinity. Do you know what I mean? So they take, this is here, it's kind of like the next term not included, in the Taylor polynomial, which is why it's f of n plus 1. Now C, we'll get to that in a second, but that's why this here is the 1 degree after n. It's the n plus 1 is the one after n. Now what is the C value? Where C is between x and a, so that either C is in the open interval, a to x, or x to a, depending on which one's bigger and smaller. Doesn't really matter. Depending on the values of a and x. This formula for Rnx is called the Lagrange form of the error term. Find the third degree Taylor polynomial of sin x about pi on 4. Okay, 1a, the third degree. So T3, right? Yeah. So we're doing T3. Now, it might help, T3 of x, it might help to first write it as general terms with the sum, and then figure out the rest. So it's from k equals 0 to 3. And what is it? It's usually the kth derivative of, now what's a? Exactly. Because it's about pi on 4. So graphically it's like we're approximating the curve around pi on 4, so around that x value, our approximations are going to be very close to the original function. So it's about f of pi on 4, and then what do I divide that by? Factorial, and then it's times x minus pi on 4 to the, okay, beautiful, well done. Now, what's fx? Yes, good. Okay, so now I'm going to give you a minute to play with that, get it in expanded form, and then I'm going to look at my notes. Okay, I'll keep doing my solution as well. So if I need to find, I'm going to eventually, when I work this out, it's going to be, when k is 0, it's just f of pi on 4, or sine of pi on 4 over k 0 factorial, which is 1, times x minus pi on 4 to the 0, which is just 1. So that's the first term. When k is 1, you get the first derivative of pi on 4. So it's the derivative of sine x. What's the derivative of sine x? Cos x. So now it's cos of pi on 4 over 1 factorial, which is actually just 1, times x minus pi on 4 to the power of 1. Plus, now I want to do in case 2. So now I need the second derivative. What's the second derivative? Derivative of cos x is negative sine x. So I get negative sine of pi on 4 over 2 factorial times x minus pi on 4 squared. Okay, so k was 0 here, 1 here, 2 here. I need to add one more term for k is 3. So I get the third derivative. What's the third derivative? What's the derivative of negative sine x? That's negative cos x. So it's negative cos, but I put in pi on 4 over 3 factorial times x minus pi on 4 cubed. Okay, let's try and simplify this. Sine of pi on 4, hopefully you know, is 1 on root 2. Plus, cos pi on 4 is 1 on root 2, divided by 1 is just 1 on root 2. Times x minus pi on 4. And then we got minus 1 on root 2, because minus sine pi on 4, divided by 2 factorial, which is 2, is minus 1 on 2 root 2 times x minus pi on 4 squared. And then minus, again, 1 on root 2, but over 3 factorial, that's 6. So it's 1 on 6 root 2 times x minus pi on 4 cubed. I don't see any benefit in expanding that. Okay? How are you going, Natalia? Is that okay? Cool. All right, now let's go to B. Hence, estimate sine pi on 5. Girls, that hence word is very important. That's telling you to use your previous approximation. So in other words, we're just subbing in this x value of pi on 5 into our previous polynomial. So, I would write for B, I would write, so sine pi on 5 is approximately T3 of pi on 5, which is 1 on root 2 plus 1 on root 2 times pi on 5 minus pi on 4 minus 1 on 2 root 2 pi on 5 minus pi on 4 all squared minus 1 on 6 root 2 times pi on 5 minus pi on 4 all cubed. Now, the fact that they said approximate and also as estimate, but also they didn't tell me to put in exact form personally, I think it's fine to put it in your calculator. So I might tell you what I got. So girls, I got approximately 0.5878. Use the error term to show your approximation is accurate to at least 3 decimal places. Now girls, error term. So first of all, what n value is my error term for this polynomial? We just found t cubed, t to the degree of 3. So we just got up 1 degree, which is 4. So we want to find, now what was it? The error notation was it R4? And then it's x to a. So that equals R4. Okay, sorry, this can just be a 3, but we have to use 4 in our power. But first of all, what's my x and what's my a? We said before, what was a? Good. So what must my x be then? Previous question, pi on 5. Because at the moment, we're finding the error for our T3 polynomial, but for x equals pi on 5. Does that make sense? So now, what does that equal? That equals the term with a degree of n plus 1, which is 4. So I'll just write it out like this first. It's the 4th degree. My term is f of 4 of some c. Now, it's okay. We don't even have to find c. You'll see in a second. Now, x is pi on 5 minus pi on 4 to the n plus 1, so that's to the 4 over 4 plus 1. Oh, no, yeah, no, n plus 1 is 4. Factorial, sorry. Second degree, the third degree was negative cos, and then the derivative of that is positive sine. Because the degree is negative, and then, the derivative of cos is negative, so negative is positive. So, it's sine of c. Don't know what c is, that's okay. And now, let's work out this bit here. We've got 4 pi minus 5 pi on 20, which is negative pi on 20. But to a power of 4, that'll be positive. So you could just put pi on 20 to the 4. Let's just do it that way. Over 4 factorial, which is what, 24? Now, okay, so that's all lovely. However, they said we want our approximation to be accurate to 3 decimal places. Good. Which means it's less than, based on a previous lesson, it's less than 0.0005. If you want 3 decimal places, you need 3 zeros. But this sine c thing kind of screws me up. But it's actually okay. Why is it okay? Sine of c. What do we know about sine? Exactly. So this thing here is definitely going to be less than, just subbing a 1 for that. Less than or equal to, I should say. Subbing 1 for sine c, so it's pi on 20 to the 4 on 24. So girls, if I can now, all you need to do is put that in your calculator. Show me that it's less than 0.0005, and we have proved that our approximation is correct to 3 decimal places. What is it? 0.000025. Yay! So I would say then, which is less than 0.0005, therefore T3x, or pi on 5 I should say, is correct to 3 dp.